I start with a little part of Fredholm theory, and not just a Fredholm theory, but some classification of compact operator. What we proved last time? We proved that if we have compact operator in some Banach space, which is infinite dimension. Yes. Then first, 0 is from the spectrum of operator A. Second, if lambda is from spectrum A, lambda is not 0, then it is eigenvalue. Moreover, it has finite multiplicity, so dimension of eigenspace is finite. And third, for any positive epsilon, there exists finite number of eigenvalues lambda such lambda greater than epsilon. And definition: A is Volterra operator if it is compact and spectrum of operator A is just only one number, 0. So it must be, yes, by first property. But from second and third items we do not fulfill because we have no other point in spectrum. So compact operator with only one number in spectrum, 0, is a Volterra operator. Why they are important? I want to remind you Fredholm alternative. What is Fredholm alternative? Fredholm alternative is that if we consider such equation in Banach or in Hilbert space, alternative Fredholm says us that there are two possibilities, yes? We have two opportunities for this equation. First opportunity, it has unique solution for any right side. On second, there exists non-trivial solution for the homogeneous equation, yes? So exists unique solution for any y, or exists x which is not 0 solution of homogeneous equation. It is second theorem of Fredholm, or Fredholm alternative. What happens for Volterra operator? What happens for Volterra operators? Answer: for any lambda complex, if A is Volterra operator, then for any lambda complex, equation has unique solution for any y. For Volterra operator, we always have the first opportunity in Fredholm alternative. Why? First, if lambda equals 0, then x equals y. Yes, it is. We have no operator A in equation. Second, if lambda is not 0, then we can rewrite our equation in the following manner. I divide on minus lambda. I divide this, if you divide this equation on minus lambda, you can rewrite it in the following form. And then look, please, on the definition of the Volterra operator. Spectrum is just a zero, only zero. So 1 over lambda is not from spectrum. 1 over lambda do not belong to the spectrum of operator A. So you have the inverse operator. So you have a solution. So there exists A minus 1 over lambda I minus. That's why we have a unique solution. That's why the Volterra operators are important. And we today begin the unbounded operator. If you have Volterra operator, then and if it has inverse, if zero is not a kernel, you have inverse operator. Yes, because from the range of operator. From the range of operator, you can construct the inverse operator. Of course, it will be unbounded due to the Banach theorem of inverse operator. But this unbounded operator has the empty spectrum. So the inverse operator for Volterra operator is unbounded operator with empty spectrum, because zero goes to the infinity. Correspondence between spectrum of operator and inverse operator. You must take the inverse numbers for numbers from the spectrum. So the inverse to zero is infinity, so spectrum goes to infinity, so it is empty. Some examples of Volterra operator. Simple example. More complicated example you can consider at home, but here we consider a simple example. The integration. In what space? You can consider it here or in L2. When we write one space, so we consider that operator works from this space to the same space, yes? First, I want to show you that the point spectrum is empty. And we know the construction of the spectrum of compact operator. Zero in spectrum, and any non-zero number in spectrum is a point spectrum. But show that spectrum is the point spectrum is empty. So we can conclude that the spectrum of this operator has only one number, zero. Of course, it's compact operator. We know by different theorems. It is compact operators in continuous function, space of continuous function, and it is compact operator in L2. Let's try to find point spectrum, try to find the eigenvalue and eigenvector. I state that we can take a derivative. Of course, arbitrary function from this space or arbitrary function from this space is not differentiable, yes? But if we have eigenvalue problem, and if we have eigenfunction, it is, of course, has derivative. Why? Because the integral is a differential function on the up or low limit, yes? Moreover, you can prove that if you have eigenfunction, it is function of class C infinity. If it exists. If exists f, then it is C infinity. Is it clear? Why? Because this function is differentiable. And you have equation. So it is function differentiable. And it is equal to its primitive. So it is function of class C2 because it is a primitive of differentiable function. So it is function class of C2 and it is equal to its primitive. So it is function of class C3 and so on. You can repeat these arguments again and again. So it is function of class C3. So we can take a derivative. So and of course, we have a boundary condition from this, or initial condition, moreover. So if you remember the theorem from differential equation theory, the theorem of existence and unique of solution with the boundary initial condition of Cauchy condition. So you need to solve this equation, but it is possible to solve. Because you can write that you have a logarithmic derivative. So f of x equals constant exponent x over lambda for lambda not zero. For lambda not zero. For lambda not zero. And from this initial condition, from this, you immediately obtain that constant c is 0. So our solution is 0, so it is not eigenfunction, because eigenfunction is not 0. And if lambda is 0, then we obtain that this equation is valid. Moreover, you can put it here. If lambda is 0, you immediately obtain that f of x is 0. So we prove that point spectrum is empty. It is compact operator, so it is Volterra operator. It is Volterra operator. Another approach, you can construct the resolvent operator for this operator. Another approach. To prove that only 0 is spectrum of this operator. You can construct a resolvent. Let if lambda is large, then you can write a Neumann representation of the resolvent. And we know that I suppose once upon a time we write the powers of this operator, yes? And then I take first term from this series apart and then write the whole series from the and lambda k dt. What, of course, we have a factorial in denominator, so the series is converged so fast. We can change the sum and integration. And what gives us the sum? What is the function? Exponent. And one additional lambda. So we can write it in the form 1 over minus lambda f plus and 1 lambda I put here. So we have a resolvent. You can forget about this, because there are no series, no expansion. We need to work with some convergence. We need to ask on question, is it converged or not? It's a finite formula. Only a question for what lambda it is valid. For any lambda which is not 0. Because you see we have lambda in the denominator. And we know that the spectrum is not empty for bounded operators. So we can conclude again that the unique number in spectrum for this operator is 0. So it is Volterra operator, an example of Volterra operator. And again, I repeat that for Volterra operators in Fredholm alternative always exist unique solution. So it is very good operators, Volterra operators. More difficult example, more complicated example is again, you can consider the following operator, but with good kernel. It is a Volterra operator if some assumption on kernel kxt. Here we need that it is continuous function in domain where it exists. So function k is a continuous for example, in this domain, in a triangle. So these operators often named as called operators with triangle kernel. Is it clear why triangle? Because if you AB, and it is 0 if t larger than x. So if t larger than x, here it is 0. And here is something. So you see that it is 0 on triangle, and maybe not 0 again on another triangle. So it is why these operators called as operator with triangle kernel. And in this space, it is sufficient that it is measurable and bounded. Measurable that is for existence of integral. And if it is bounded, then again, you can show, for example, that how you can show that it is Volterra operator. You can find spectral radius by formula. Again, you can find the estimation on the powers, on the norm of the powers of operator, and you can show that it is have a factorial decreasing. So then you can conclude that this operator is. So another name for this operator, quasi-nilpotent operator. But quasi-nilpotent operator, the operators with the 0 spectral radius. But it cannot be, for example, compact operator. Volterra operator is always compact operator. It is some class, subclass of compact operators. Okay, that's all. That's all about compact operators. So we begin short introduction in the theory of unbounded operators. Unbounded operators. Do you remember the Hellinger-Teplitz theorem? No. So I remind. If A is linear operator in Hilbert space, and for any x and y in H, we have such property. Later we name this operator as a symmetric operator. Then theorem states then that operator A is bounded. Okay? Remember? We will prove it with the help of Banach-Stengauss theorem. With the help of Banach-Stengauss theorem. Example. So, what is the conclusion from this theorem? Unbounded operator cannot be defined on all space. So, this class of operator is very important from quantum mechanics, yes? If it is bounded, then it is self-adjoint. But for unbounded operators, we obtain additional class of operators, symmetric operators. Symmetric operator is not, may be self-adjoint, but maybe not self-adjoint. Again, example. Consider operator, we very often consider this example. It's so-called impulse operator, yes? Impulse operator in quantum mechanics. Where in L201, of course, we know that it is unbounded operator. It is unbounded operator. Because if you consider Fn sine Pnx, the norm of Fn sine squared, like this. Oh, sorry, this. The norm of this operator is this. And if you obtain this, the derivative is cosine. The cosine has the same norm, and you have in a numerator the increasing number n. So it's 10 to the infinity. But of course, you can check that it is have this property if you consider some additional assumption on domain of operators. So, but from Hellinger-Toepler theorem, we conclude that this operator cannot be defined on all space L2. Because if you define it on all space, it must be bounded. We check that it is unbounded. So this operator must have domain. So any unbounded operator described by two objects, how it acts and what is its domain. More or first, what it is domain and how it acts on this domain. For example, the typical domain of this operator is functions from the Sobolev space with the zero at the ends, vanishing on the ends. In Sobolev space, we can define the values at points. So it's easy to check that this operator AFG equals EF prime G X. And if you integrate by parts, you obtain this formula, and you say that this non-integral part is zero by these values. So, and then you put the imaginary unit under the conjugation and change the sign. So it is just this. So you have this property, but operator is unbounded, so it must be domain. Must have domain. Moreover, this operator is not self-adjoint. It's not self-adjoint because the adjoint operator has another domain. Later we consider the adjoint operator to this operator, but you can see that you have this symmetric property arised only by the assumption on function f. You have no boundary condition on g. So you can write it as AFG equals FA star G, and the domain of operator A star is just Sobolev space without boundary condition. Without boundary condition. So the domain of operator A star is larger. It is symmetric but not self-adjoint operator. It is symmetric but not self-adjoint operator. So our further investigation, of course, will be in Hilbert space. What we have? We have H Hilbert space. And we have operator A, which is linear in this operator and unbounded. Unbounded. And we have a domain of operator. By definition, domain is just such function from or such elements of not the largest, not possible, as large as possible. You can consider motion. You can consider this operator not in Sobolev space. You can consider it, for example, on this space. It is again defined, yes? Again defined, but with boundary conditions for the symmetric property, So it is not the largest possible element in our space, Hilbert space H, but it is such such elements from Hilbert space H for which Ax belongs to Hilbert space H again. So if X belongs to the A for domain, then Ax is defined and belongs to H again. So we have a correct operator from H to H. From H to H. So so-called the natural domain is the possible largest domain, of course. But it is sometimes have no efficient, effective description of this of the largest domain. So definition, graph of operator. Graph of operator, gamma capital of A. It is pair XAX. Maybe I write it in these brackets. Because with these brackets we can confuse with scalar product. Yeah? So I write in figure brackets. Where X, where it belongs? It belongs in Cartesian product of H and H. Yes, it's pair. X and AX. And X is from the A. So it is just a definition of graph of operator. Of course, it is a linear subspace in Cartesian. Yes, because our operator is linear, so it is linear subspace in Cartesian product of H and H.
It's a Cartesian product.
Yes, Cartesian product. Because it is pair. X and AX.
Like said theoretically, this is actually the operator A itself, because this is how you define a function.
Why? Why itself?
But
it's not a graph. It does not coincide with graph of function, for example.
like said theoretically, a function and its graph is the same object, because a function.
Yeah, but it is not. It is not. For operator, it is not. Yes, we can. You can consider number-valued function. Yes, you can consider. You can really obtain that. F and its graph is the same. Yes, of course, as a description of some object. But here it is not. We do not consider graph as a description of operator. We can consider so-called graph norm. Graph norm. There are two different formulas, but they are equivalent. Standard definition of graph norm is based on the scalar product in Hilbert space. So you can take it, because it is Cartesian, so you can take scalar product x of x, it is x square, plus scalar product ax on ax, and take a square root. And take a square root. So this norm, graph norm, is based on scalar product. But of course, it is equivalent to the following. Of course, it is not convenient formula because you need to work with squares and square roots. Of course, it is equivalent to this norm. It is not based on a scalar product, but they are equivalent, of course, yes?
Maybe ignore the other term.
And this is more convenient because it is easier formulas. We will use these formulas for the graph norm.
That's like just a restriction of the norm on Cartesian product.
Yes, and on axis from domain, of course. It is graph norm on the element of graph. So pair x and x belongs to the graph of operator. So I think it is easy there. It is clear that they're equivalent. It is just for numbers, a plus b.
But we assume that x is orthogonal to 8x.
What we assume?
In the first equation, in the square root.
It is based on just on the scalar product. Because this is x squared and this is scalar products of this element. We know we start from the Hilbert space.
Okay.
So it is a more natural way. But this formula is not convenient. So we consider the equivalent norm, graph norm. But what happens if operator is bounded? We know that the boundness of operator, of linear operators, is equivalent to the continuity of operator. Operator is continuous. That what we can do? We can do this is important thing for bounded operators. But for unbounded operators, we cannot do this. Yes? But we want to do this. So the question, exist such operators for which this property is in some sense preserves? And this gives us the definition of the closed operator. So definition. If graph of operator is closed subset in Cartesian product, but closed in graph norm. You can rewrite in the let's rewrite this definition in terms of sequences.
Can we say that this has to be convergent series?
Hmm?
This has to be convergent series x. Which you approximated as x plus ax.
If you want to consider the x n y n, with figure brackets, tends to the x y. Simultaneously, xn goes to x in this, and yn goes to y by this. And this question was?
This has to converge, right? The sequence. That's how we can say it's closed.
So I write that. I just write what it means.
Yeah.
I just write this What it means? If xn lies in domain of operator, yes, and xn tends to x, axn tends to y, then x from domain of operator and y is ax. It is the definition of closed operator in terms of sequences. For example, operator A, which I write here, is closed operator. Closed operators are good operators. You can do this on the domain of operator. And in graph of operator, in Cartesian product, in graph norm, you have convergences. Operator can be unbounded, but closed operators preserve convergences. So it is good operators. It is good operators among all bounded operators. Let's, again, some example. It is identity function, constant. I write this because I don't, this can confuse with functional. Yes, but this writing I want to emphasize that this is operator. We always obtain a constant function. This constant depends on the value of function 0. Okay, what you can say about closure of this operator? Or maybe, oh, it is not Hilbert situation, let's correct. I write this, but in L2, this is not correct object, yes? But, okay. We consider it on a domain. On continuous function, for continuous function, the value at points is good object, is well defined. What you can say about the graph of this operator? Or is it operator closed or not closed? It is not closed. It is not closed because let's consider such function. What is what these functions gives us in graph? I don't write this precise formula. I think it's clear what happened. But what you can say about this pair? Yes. Yes. What is the limit of functions fn in L2? What is the limit of fn in L2? 0. So it tends to the element 0, 1. For linear operator, it is impossible. Such element cannot lie in graph of operator if operator is linear, because linear operator on 0 gives us 0.
But the limit is not in the space of continuity.
It is not, it is not, it is...
I understand, but the limit, I think, is not in the space of continuous function. If in 0 will be 1, and the rest will be 0.
But in L2 it is 0. In
zero.
L2,
Only measure
yes. In L2 it is 0.
0.
In L2 it is 0. In continuous function we have no limit. But I correct our situation. So the limit of this function in L2 is 0 function. Almost everywhere. From this point of view of L2, it is 0 element. You can change function on any measure, on any set with 0 measure. Yes?
I have a question. Maybe I misunderstand something. So if an operator has a closed graph, then it preserves convergence of sequences.
Yes.
This means
On its domain. On its domain,
that
yes.
means sequential continuity.
Yes.
And
Not continuity because it is unbound. No, yes, it is something analog of continuous
Sure,
operator.
if you consider the metric, the norm metric on its domain, that will mean sequential continuity, and sequential continuity is equivalent to continuity in metric spaces. So that means that
It is, but it is continuity in graph norm. It is continuity in graph norm, not in norm of a space. Norm is norm of space. In graph norm. But it means that if operator is closed, then graph norm is corresponds to the origin norm in a Hilbert space.
yeah, because I was thinking
But if operator is not closed, the graph norm is bad object. So this operator is not closed. Moreover, it is not a closable operator. So you must understand that closed operators are good operators. So they preserve convergence on the domain of operator. By definition, just by definition of operator, of closed operator. If operator is not closed, they are good, bad operators, and humanity do not consider unclosed operators. But if operator is not closed, what we can do? What we can do? So the graph of operator is not closed set. You can consider the closure of this set. So let's consider there can be two situations. Can be two situations. First situation. If is graph of some operator then we define this operator as a closure of operator A. If the closure of graph is a graph of some operator, B, for example, then B is closure of A, and we denote it as this.
But you see, me, if this is the graph of some operator, this operator is unique.
Yes.
That's
But second possibility, the closure is not graph. So your operator is unclosed and it has no closure. It is bad operators. It is bad operators. We do not consider such operators. What means it is not a graph? We know that the graph of operator is linear subspace. But what can happen if it is not a graph of a linear operator? That means the element 0, y belongs to the closure and y is not 0. This example. You see that this operator is not closed and it has no closure. Because in closure of graph exists element which cannot be an element of a graph operator. Because linear operator on 0 must give us 0. And here we have 0 and non-zero element. So it is typical situation for unclosable operators. If operator is unclosable, by definition, the closure of graph is not a graph of function of a linear operator. So it contains such element. Here an example. Okay?
I didn't understand.
What?
This example.
I consider this operator NL2 in Hilbert space, such operator, with such domain. It is well defined, yes? I consider such sequence of functions. These functions in L2 go to the 0 function. By definition of my operator, this graph, element from graph, looks like this. Fn and 1, yes, because here 1. And I want to consider the closure of the graph of operator. And I see that by definition of closure, I have a limit point. It is a limit point of graph, so it lies in the closure. But it lies in closure. But this element cannot be a graph of a linear operator. Because linear operator on 0 gives a 0 by definition of a linear. So this operator is not closable. It is not closed, but it is not closable. But
if it gives 0 here, what it gives?
This element cannot be in graph. That's all. So is it clear that the limit of this sequence is this element? But it is not in graph of a linear operator, of any linear operator. Okay? For example, you can consider previous operator with domain with such domain. It is not closed operator. But if you consider the closure of this operator, you obtain that in L2 you immediately obtain here this. Because it is the largest closed subspace when we can define the derivative. And derivative, by definition, you can define this operator on such class that derivative lies in L2. By definition, it is Sobolev space W1, 2. So it is closable operator. This operator is not closed, but it is closable. This is a closure. So let's write definition. Is graph of some operator when A is closable operator and its closure such that the graph of this coincides to this. Okay? Okay. How you can define now the joint operator? So you have a linear unbounded operator. How we define? Can we define the joint operator? Can we define the joint operator? Let's consider linear operator in H. But additional new property we demanded always with a dense domain. Domain must be dense in L2. Then first I define the domain of a joint operator. It is such element H in H small and H capital such that is a bounded functional in H, X in dA. It is of course linear, yes, by linearity of scalar product. And if by this theorem, what you can say? If it is linear functional, how you can write it?
A product or linear product.
It is then it is x z, yes, with some element z by this theorem. And then you define
Here H is the Hilbert space. Capital
hmm?
H is the Hilbert space.
Is here. We always work now, just now, we always work only in Hilbert space, on scalar product, a joint operator. There is example, so operator A can be very bad, for example. So there is examples that the domain of a joint operator have only one element 0. Of course, the domain of a joint operator is not empty. For example, 0 always lies in domain of a joint operator. But there are examples that, for example, only 0 element lies in domain of a joint operator. Why we demand this property? Who can explain? Why we demand this property? If the domain is not dense, then this element z is not unique. Because you can write non-zero element, if it is not dense, you can find element which is orthogonal to the domain. And up to this element, you can add it to z, the orthogonal element to domain. So then element z is not unique, then you have no operator. So it is necessary condition, and sufficient, if you see, to define in correct way a joint operator.
Then we cannot write X as A star H.
Yeah, we can't define correctly. It is not unique operator, but we want to have a correct description and uniqueness of this operator. So we always demand this property. We consider operators with the closed domain, with the dense domain. Sorry, with the dense domain.
I just want confirmation. By the W they mean dense as it's also closed, right? It's also closed.
No, it is dense only. For example, we consider operator AF, F01 on domain dA, which is continuous function. Of course, continuous function dense in L2, but it is not closed. Again, another example with this domain 0. It is that a short note for the vanishing cadence, W with 0. It is dense in L2 in norm of L2. It is again a dense set, but it is not closed in L2. If you consider the closure of this set in L2, you obtain a L2. Without this property, you can't define correctly a joint operator. And again, by this definition, you see we obtain immediately almost the same definition as for bounded operators. Yes, we have property that AXH equals XA star H by definition. But additionally, we need to describe the domain of operator. The domain of operator. Because it is just such elements for which we can act by this operator. It is bounded functional, there exists Z, Then we define the action of operator z equals to a star h. We just define it. In theorem, we have linear operator with dense domain. Then we know that the a star exists. Yes? But a joint operator always closed. A joint operator always closed. The proof is simple. Let's consider operator it is like rotating. Rotating operator on 90 degrees, yes? So linear subspace go to linear subspace. Let's show that this identity is valid. The graph of a joint operator coincides with the orthogonal complement to this. And what you know about orthogonal complement? Always closed. All subspace. So if we show this, we immediately obtain that the joint operator is a closed operator. So by definition, we know that this property is valid, yes? We can rewrite it as and then let's write x minus here. Can we write this equation as this property? In how define the scalar product in a Cartesian? If you have x1, a1, scalar product x2, y2. Cartesian product of Hilbert space. By elements. By definition, it equals x1, x2 in H plus y1, y2 in H. It is just by definition of scalar product in Cartesian product. So let's consider, let's check this property. Let's check this property. I take it away. is this equation is the same equation? Compare it, please. Multiplicate with -1. Multiplicate this on -1, you obtain this. Or multiplicate this on -1, you obtain this. Is it clear? Is it clear or not?
I think we prove that if
I prove this property. I prove that this element orthogonal to this element by definition of a joint operator.
intuitively, I think we prove that
And here I write the inner product for this element and this element in Cartesian product. This first part, scalar product with the first part for first argument, and second with the second, and plus.
yes, I know that.
And I see that this is the same as this. And this is true by definition of a joint operator. But equality to 0 is just orthogonality. The equality to 0 is just orthogonality.
What I'm thinking is that we prove that.
So we prove that, but this element is just equal to this.
Yes.
And this is element from the graph.
Yes.
So we prove this.
So we prove that.
The graph of, and this is element is from graph of A star, if you see.
I think we prove that gamma A star is inside this.
No, just coincide, but the domain of A is dense. So it just coincides with this. It just coincides with this. And the orthogonal complement is closed. Closed. Following theorem. Let's again consider linear operator with the dense domain. And in further our investigations, always we take this property. The domain must be dense because it is a necessary and sufficient condition to define correctly a joint operator. Then and this is moreover, it is orthogonal. When we when we consider Fredholm theory, we prove this equality for operator A, identity minus A. But we never use the boundness of operator when we prove it. Yes? Need I repeat the proof of this theorem? Or not? When we work with Fredholm operators, we prove this property, but without this. Without this, because we prove that the range is closed. But for arbitrary operator, range cannot be closed. Moreover, we consider unbounded operator. But when we prove this property, we do not use boundness of operator. No, again, let's repeat. First, show that if x equal to kernel and y belongs to the range of operator A, then ax equals to 0 and y equals to A star z for some z. Yes? Then x a x y equals x a star z equals a x z, it is 0, so it is 0. So we show that these two subsets are orthogonal. Second step. We know that by Cauchy-Bunyakovsky inequality that the scalar product is continuous function. So then we immediately obtain that to the limit points. It's orthogonal to the closure. Is it clear why? You take a limit point for this, so exists element from this which converts to the limit point. For any element for this, we have 0. So in limit, we have 0 too. Okay. And the third step, we need to show that it is all space, yes? So third, if we suppose that exists H with orthogonal to the then for any x from the domain of A y it is 0. Y it is 0. It's orthogonal to kernel and orthogonal to the range of a joint operator. So what we can say about this scalar product? Let's take by definition, let's
But you said that we have that the kernel is orthogonal to the range or to the here.
oh, sorry. I'm sorry. Because we see that it is not true. This is true.
Okay.
This is true. The kernel, again, this is the same. So let's, if show that the orthogonal, that the kernel of a joint operator and the range of operator are orthogonal. Why it is so? Sorry. So it means that x, y equals az for some z. For some z, so x a az equals a star x z, it is 0. So x orthogonal to y. And now if then kernel of a joint operator orthogonal by, again, by this is second, by continuous of scalar product. By continuity of scalar product. And third, if we suppose that exists H from this space, then for any x of domain, it is 0, yes. And now it is, why it is 0? Because H is orthogonal to the range of operator A. Yes? So it is 0. Then we write it following. It is dense in H. So immediately obtain that A star H equals to 0, so H is belongs to orthogonal to the kernel of operator A star, and it is orthogonal. So it is is 0. So for unbounded operator, it is important the order of kernel and range. The kernel of a joint operator and range of some of the operator, and the range of operator. And then theorem, again, A is a linear operator in H with dense domain. Question when this operator is closable. When this operator is closable. A is closable if and only if the domain of a joint operator is dense. What it allows to do, and then the closure of operator we know that this property is necessary for to define the joint operator. So we can consider second adjoint operator. For unbounded situation, it is not an operator A. For unbounded situation, if you consider an unbounded operator, it is not operator A in general situation. Sometimes may coincide, but in general situation, it is not an operator A. But it is just a closure operator.
Sorry, I think if the domain of operator n is whole space, the domain of A star is closed.
But by is domain a whole space, for example, if it is symmetric operator, by Hellinger-Toeplitz, you immediately obtain that it is bounded. So only domain only dense. It is not whole space.
Does a self-adjoint operator domain of self-adjoint operator?
No, 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 no. Again, let's. Then later we prove what I state. We consider this operator with this domain. It is symmetric, but it is not self-adjoint. But a joint operator, F,
And if this closable,
hmm?
is this
They are closed. These both operators are closed. But it is not self-adjoint. Here the operator A, it is closed operator. So it coincides by this theorem, it is just coincide with this. But it is not self-adjoint, because a joint operator has another domain. Just what I want to, the most important thing in this theory for us, for you, understand what you can do with symmetric operators. Unfortunately, it is difficult to understand for you because you have physics, yes? Physics do not distinguish symmetric operator and self-adjoint operator. They always consider only self-adjoint operator, but there you see there exist symmetric operators which are not self-adjoint operators. I understand that for physics these operators are useless. Symmetric operators which are not self-adjoint. They are not correspond to some physical situations, yes? The self-adjoint operators are useful, yeah? Of course. But symmetric operators are useless. But they exist. But for good operators, you can construct self-adjoint extension. It is a lot short spoiler of our theory, but about one lecture additional, we show how to construct what we need for operators to construct a self-adjoint extension. Okay, because if you consider the definition of symmetric operator, you can understand that symmetric operator is just operator for any f, g from domain. It is definition of symmetric operator. Symmetric operator is operator for which this equation is valid. But we know that this equation is valid another for any f from domain A and for any g from domain of a joint operator. So if you compare these two lines, you can construct another definition of symmetric operator. Symmetric operator is just operator with this property. It means that the domain of A includes in domain of A star, and on the nearest part, the actions of operators are the same. This is dA belongs to dA star by this. And A star on domain of A is just A. It is another definition of self-adjoint operator, symmetric operator. So the closure cannot be self-adjoint. For example, for this operator. This operator is closed, and this is the joint operator. It is closed. We prove that any joint operator is closed. But its closure is not self-adjoint. Its closure is not self-adjoint. Later, we construct all self-adjoint extensions for this, like illustrations. When we finish the theory, we construct the all self-adjoint extension for this operator. And it is important to know how to construct self-adjoint extensions. So, following theorem. What about following theorem? This theorem. I don't prove this theorem. Let's prove. What gives us the second power of operator W? I remind that W xy equals minus yx. So it is minus identity, yes? It is minus identity. Let's I take it because along calculations. By this assumption, we know that the adjoint operator exists. Yes? What you can say about this? We know what means the graph of adjoint operator. Orthogonal, yes? And this is linear operator. So it is you can put it into the orthogonal. And it's just a minus identity for linear. And now take what gives us this operation. The orthogonal to Yes, we proved it. And this is and this exists just to this assumption. And what gives us this? Closure. And we see that the closure of graph is a graph of some operator, which exists. And by definition, this is graph of what operator? A star. Be healthy. So let's again consider our example, simple example. Can you describe the joint operator? Can you describe the joint operator for this operator? What it is domain and how it acts on the. We know what? In this situation, the kernel of operator, a joint operator, is orthogonal to the domain of operator A star is such function g from L2, 0, 1, for which A f g is bounded functional. And we know that this must be bounded functional. Here A, F, G, yes? So it equals but if it is it continuous functional on domain? Is it continuous functional on domain? No. No. The domain is continuous functions. Again, consider such sequence. Functions go to 0 in L2. But fn of 0 is 1. Is it continuous function? It is not continuous functional. What is way to make it continuous? With the help of function g. If you have this object, it is not continuous functions. You have a unique way to take away this object with the help of function g. How? Again, if this exists, object, if you write f of 0, it is not a continuous functional. How take away this object? if and only if it is linear, it is a continuous function, if and only if this is 0. This must be 0. Because if it is not 0, so you have this. And you see that this is not continuous functional. So it is continuous function, bounded function, if and only if so G orthogonal to 1. But 1 is the range of operator A. Yes? And we know that the orthogonal complement is a kernel. So this function lies in what? Immediately. Because this belongs to the range of operator A. Yes? So G is kernel. So joint operator looks like following. Domain of operator is function G in L2 0, 1 such that G orthogonal to 1. A star G equals to 0. Very simple joint operator. It is 0 operator on domain. It is not typical situation, but it is typical for operators which are not closable. It happens because operator A is not closable. It's bad operator. You see that the domain of a joint operator is not dense. It is orthogonal complement to L2. It is not dense. If you it is closed subspace because it is orthogonal complement to 1. It is closed subspace. So the closure coincides with this set. So the domain of a joint operator is not dense, so we can construct a second adjoint operator. It is not correctly defined. So operator A is not closable because the closure of operator A is the second adjoint, but the domain of a joint operator is not dense, so it has no second adjoint operator. Okay? One additional theorem. When exists inverse bounded operator from the range, of course. We consider unbounded situation, so our operator is not B action. Exists only if. We prove that then the range of operator is closed. The same is valid for unbound, but when we prove it, we use that operator is bounded. So it is continuous. But this is valid, again, for the closed operators. Because if operator is closed, you can repeat all the same arguments for the bounded operator. By definition of the closed operator, it preserves convergence on the graph. You immediately obtain the same situation. Yes, we prove it. But this is it clear? The proof. It is not long. Let's prove and make brief. This. if exists bounded operator, then for any y from the range of operator, a minus 1 y yes? Of course, if operator, if exists inverse, then the kernel of operator R is 0. Yes? If exists inverse operator from the range, left inverse operator. Left inverse operator, so we have, it is linear, we prove it, and kernel is 0. So there exists unique x that y equals to ax. So we immediately obtain that so what we take as constant? What we take as constant? This, okay, and this. The kernel of operator is 0, so we immediately obtain the exist left inverse operator from the range to H. And why it is bounded? Why it is bounded? Because you can write this in this manner, yes? And this means that a minus y is bounded. But it's defined not on all space, it's defined only on range. So let's take a break, make a break. So you see that theory of unbounded operators more difficult, yes?